Hello, how are you doing, differential equation kids? It is time for another lesson. I know you're super excited. So we have some book problems, 3 through 8, for you to do on page 271. Starts on page 271 and goes to 272. Here is a warm-up for you to try of the previous examples. So I am not going to go through this with you, but I will give you the answer. So if you do our power series expansion, hopefully you can tell that the expansion is around, right? It is around x equals 0 here. And then it is an initial value problem. So the answer I got was y equals so see if you can get there. And right, this process is, once you start getting used to it, there is just the summation work and the index work and the power work and then algebra, really, right? So, but we've kind of been making some assumptions, right? A Taylor series expansion for a solution. Remember, differential equations is kind of, all of these techniques, right, are, undetermined coefficients, our variation of parameters. We really are starting off with a guess as to what a differential equation solution would be, and then seeing if it happens to work out. So it's kind of weird in a sense, and that in reality, these differential equations there's so many different answers, different solutions that are right, and you're just hoping to stumble upon one that works. And it just, the more you do these, and I have to say, this is the first year I've taught this, so I'm rusty. So I feel like my recognition of the type I should use or what would be best to do is rusty as well. And then for you also, you're doing it for the first time, so it seems kind of weird and like shots in the dark. But I just want you to realize that that's normal. Right? That is normal, because differential equations isn't like, oh, if I do this thing right, I will definitely get an answer. There are some that never can be solved. Right? We did that. I told you that in BC calculus. Right? If you give me any function, I can differentiate it. But if there are some differential equations that there is no analytic solution to, and by analytic I mean like I can just write it as a write it as an explicit rule. And with power series, I'm still kind of sacrificing and saying I have an infinite rule. But I really have glossed over the fact that when we're doing Taylor series, we've got an extra thing to worry about, right? We have radius of convergence, and what if, since we're Taylor series, are built upon derivatives and derivative rules, there's an inherent assumption that I've got continuity and that I don't have any corners or cusp or anything to deal with. So I've purposefully glossed over that while we just practice the mechanism of generating a power series solution to differential equations. But today I want to talk about maybe when things don't work out so well. So a singular point is not a great thing. So first I want to define analytic. Oh, I don't know why that F is so weird there. Is said to be, I guess it's not an equation, right? Ew, this makes me sad. Is said to be analytic. Analytic sounds like such a fancy word, but it just means everything's okay. Everything's good, right? I don't have any discontinuities. I'm continuous. I'm great. So if the center, right, the center of my expansion, we call some x number, if my function f is analytic around the center, its Taylor series exists and converges to some function, right, for all x in an open interval. including, of course, my center. So that's the radius of convergence. And honestly, if for all of our answers that we've done before, we could find the radius of convergence with, shocker, the ratio test, right? But we have to write everything in summation notation, which isn't that always that easy to do. So you're not responsible for that. But we are going to be responsible for this idea of what if things aren't so great around my center. So firstly, all our familiar functions of calculus are good to go, right? Everything's good, analytic, good to go. Sine, cosine, e, all our polynomial functions. Excuse me, and all our rational functions too, except of course where the denominator is equal to 0. So that's nice to know. So this idea of a solution, let me see if I can do it. If I have some function f that I believe is a solution to a differential equation. So let's say, right? So there's this solution is, this graph is f, a solution to a differential equation. And say this is my center. And so I generated a Taylor series approximation to approximate this graph. And everything's cool around, right? Around my center. But what if things weren't cool around my center? What if, oh rats, I didn't really mean to do that. What if I had a discontinuity there, right? What if my function didn't exist actually at one freaking point, happened to be my center, right? Where I was my Taylor series expansion. Or what if this scenario? What if I had something like that, where I at my center? Or what if I had something like that at my center? Or lastly, what if I had something like that at x sub 0? So these are all issues, right? These are all sad situations for my calculus, especially when I'm if I'm dealing with power series, right? Where the power series expansion is built with derivatives, and derivatives at all of these x sub 0s are going to have a problem, right? Even when I've got continuity. So, I may have continuity. Well, let me tell you that. What haven't I used? I guess my blue, right? There's nothing to be done. Nothing to be done here. So I'm still sad. There's nothing to be done here. I'm still sad, right? A Taylor series expansion around, it just is not going to work. But here, look at what, even though I have a derivative problem, I do have a derivative problem, but what's true about the neighborhood around x sub 0 here. That is not true about the neighborhood around these x sub 0s. Let me give you a hint. It starts with an L. La 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 limit. Sorry, I'm going a little stir crazy. So the whole idea of, well, if I have some issue here, if I have a limit that is finite, a limit of the function that is finite, I can kind of fake my way through the Taylor series, right? I'm going to be okay as long as I identify there's just one and only one point that's an issue. But here, this limit does not exist, so there's nothing to be done. This limit on one side or the other is an infinity, right? So nothing to be done. So that's kind of conceptually what we're going to be thinking about with singular points. So they call these, all of these are singular issues, right? I have an issue. So think about singular as having an issue at x sub 0. But this is called a weak, and usually weak is a bad thing. This is weak singularity. This is weak singularity. And if you have, I guess you call these strong, but I don't know. There's nothing to be done about these, so we don't bother labeling these. But here, or in terms of singularity, these are called, if it's a weak singularity, we're allowed, we can still manage with our power series, and we can just talk about neighborhood around our center, and just identify the place where we have the issue and say everywhere else around there is okay. So I hope I haven't confused you more than with my drawings, but this is what I what I picture in my head. So before we deal any more kind of with this idea of a limit, first let's just talk about identifying, finding, and classifying. And classifying is going to have to do with this issue of weak, but we're not going to use that term. But of the two conditions where we have where we're able to fake our way through. So I've got an issue. See how embarrassed we are? We have an issue. So how do we know that we have an issue? Step one, you need to get your differential equation into standard or normal form, right? And we've dealt with this before, but sometimes we just get kind of lazy with, yeah, we know we're supposed to have a coefficient of 1 in front of y prime, but it doesn't really mess too much with our math until now, right? So I've highlighted p of x here. If you have any function in front of the second derivative, you need to divide through to get rid of it. Now remember, technically you're dividing this by p of x too, but 0 over p of x is still 0, so I didn't bother writing it. So step one, get a coefficient in front of the second derivative. Now I'm highlighting or putting a box around those two ratios. Personally, I like to call these ratios A and B, but your textbook doesn't, so I'm going to use their notation. I'm not particularly fond of it, though. They call the ratio after standard form in front of y prime, they call that little p, and they call the ratio in front of y little q, right? Like I said, I don't particularly like those labels, but whatever. So, step 2, every x value that does not create 0 in these denominators, so in other words, I'm looking at capital P of x. What makes capital P of x 0? If nothing makes P of x equal to 0, for example, if P of x was x squared plus 3, nothing makes P of x equal to 0, then every x is what we call an ordinary point, and I've got no issues at all. Done. We say then that the solution then is analytic at every center, right? No matter what I choose. Ordinary, if everything's ordinary, analytic. And x sub 0 is an ordinary point. However, if there are x values that do make p of x equal to 0, for instance, if p of x was x minus 3, right? Every x that does create 0 in the denominator of little p and little q, in other words, what capital P, do you see why I don't like using little p and little q? What makes p of x equal to 0 is singular. So you are either ordinary or you're singular, and that is only dependent upon whether you make the function in front of y double prime equal to 0, because in order to get into standard form, you're dividing by that function in front of y double prime. If you are singular, singular points can be classified as either regular or irregular. If we have an issue, if we're going to have an issue, we would rather have a regular issue. That comes from our weak singularities. Irregular is the ones we can't do anything about. All right, so after I determine what x's create singularity or are singular points, then I have to worry about whether those points are regular or irregular, and this is going to involve my limit work, although I'm going to show you a shortcut to that. Before you worry about the limit or the shortcut to the limit, you do need to simplify these expressions. So you can use my shortcut. And what you're trying to do is simplify so that there are no matching factors in the numerator and denominator anymore. And then you're going to look for the power of each singularity point in your denominators. So that's why you need to simplify first in case there's any matching factors. So I need to look just at my denominator and see what is the power, how many times do I see x minus 3 represented in each one of my denominators. If the factor with your singularity point is only represented once or just to the 0 power or not at all in your first fraction, and your singularity factor is represented in the second factor twice, once, or to the 0 power, then you have a weak singularity point, and then you can say that your singularity point is regular. Formally, this needs limit work. I'll show you what both of these look like. Otherwise, your singularity point is irregular. If you have too many factors, if you have more than one of your singularity factor in the first denominator, or more than 2 in your second one, and it doesn't matter. It only takes one condition to be burst, and then you are irregular. So again, this work here, step 5 and step 6, is to avoid limit work. So let's do some. So find all singular points of this second order differential equation and then determine whether you're regular or irregular. So here is my first example. So hopefully the first thing you're going to do is determine if, what do you have to divide by? So hopefully you can see that, and that you need to divide by 2x squared, right? This is my capital P of x So when I divide through, and I just simplified here, right? This is what I got. Right, so I kind of did the simplification and the dividing through in the same step. So I said little p was in front of y prime, and little q is in front of y. And I can conclude that x sub 0 is a singular point. So why can I conclude that is because not doing limit work, taking the shortcut to the limit work, I said to myself, x is equal to 0 is the only thing that made 2x squared equal to 0. And so what I did was I said x minus my x sub 0 to the n in P of x. How many times do I see that? Well, there's x minus 0 to the first. Truth? Here in Q, this is 2 times x minus 0 squared. So in little p, the factor with my point of singularity only appears to a power of 1. And in the y term, my factor x minus 0, which is the point from singularity, appears twice, which meets the condition to be, well, firstly, meeting the condition to be a singular point is met up here. I make P of x equal to 0. But since in P of x I only saw x minus 0 to the first, and in Q of x I saw x minus 0 squared, my singular point is a regular singular point. Okay. So this is all I need to do for the homework. And the only thing is you don't have to do the limit work unless you're asked. So again, you're not going to have any tests, so you're not going to be asked. But if we were giving you an actual test, we would ask you to verify the fact that a point was a regular singular point with limit work. So I'm going to go through that at least one time with you. But for the homework you want to practice, you can just use the shortcut. So here's the limit work. What you're really doing is you're saying the limit as x approaches, this is the neighborhood idea. So you're basically asking, does the function behave around the center, or does it swoosh off, or does it jump? Right? So in the neighborhood around the center, if you take the limit and multiply the limit times your P of x, this is prior to simplification, right? I think. That will equal, no, it doesn't matter. After simplification, I'm sorry. So what this equals is the limit as x approaches 0 of my point of singularity, my factor with a singularity, times P of x. And of course this simplifies, right? Because this is really just x to the first times negative 1 over 2x, right? And those cancel, and so I'm putting in 0 to no x. So my limit is just negative a half. I don't really care what my limit is. It's finite, right? It's not an infinity or does not exist. Then you're testing Q of x. And the whole idea of kind of why you do it squared, I don't know, it's kind of an analogy to, you know, when you're doing like partial fraction work and you have a repeated factor And so you do your partial fractions, say like you have x plus 2 squared, you split up your partial fractions and your one denominator is x plus 2 and your next denominator is x plus 2 squared, right, to just take care of the repetition. Well, this is the same factor, x minus my singularity point. So that's why in the next one I look at it to a factor of 2. So I'm really doing the limit as x approaches my point of singularity of my factor with my singularity point squared times my q of x. So if you notice here, what happens is, right, this is really x squared. So the x squared cancels out with this x squared, and I'm left with just my x minus 5 over 2, applying my limit by putting in the 0. So I get 0 minus 5 over 2, which is negative 5 halves, which is also finite. So here, the fact that the function behaves, both the, right, multiplying times my y, multiplying times y prime, both behave around the point of singularity, and so we can say that the Taylor series is, right, you only have to worry about that point, that we're okay using the Taylor series around, in the neighborhood around the center. Because the limits of both of these ratios are finite, I can say that 0 is a regular singular point. Again, this work is the reason this works, right? Of just saying how many times does it appear, okay? This is just quicker and faster way through the limit work. This is the more formal approach to it. All right, so let's try again. You might want to pause the video and see if you want to do this your own, see what you get. Find all singular points. So remember, that's when find all singular points is where you're taking the function in front of y double prime and finding all the x's, if any, that generate 0. Then you are testing to see whether any of those points are regular singular points or irregular. So my p of x is right there. So you're dividing everybody by that. I'm going to write it like this. So the first thing I'm looking at is what makes this, and remember I did divide here too, right? So I divided, and I'm looking at what x's create 0 in these denominators, and hopefully you can see that x equals 0 and x equals 2 are your singular points. So once they are singular, now I want to know about the factor with my singular point in it. So if I say x minus 0 to the n and x minus 2 to the n, right? If I now simplify up here, this x cancels out here. This x plus 2 cancels out here. And x to the 0, right? And now that I've simplified, how many times does that appear in the denominator of y prime? It don't. and n equals, how many times do you see the factor x minus 0 in the denominator in front of y? There, right? This meets the conditions to be regular. Yes? Right? So the singular point x equals 0 is a regular singular point. Now what about x minus 2? In y prime, I see x minus 2 how many times? I don't care what happens here. This breaks the rules to be regular, therefore x minus 2 is singular, but it is an irregular singular point. And that's all you have to do for your homework, is determine where your singular points are and if they're regular or irregular. You don't have to do anything else. So again, I'm going to go ahead and do some limit work with this last one, but that's the last time I'm going to show the formal verification. So we want to get to the same conclusion with limit work. So if I say the limit as x approaches my point of singularity of the factor x minus my point of singularity to the first, and then I also need to do the limit as x approaches 0, my point of singularity, times the factor with my point of singularity to the second for my y, and to the first for my y prime. And I can already simplify this. I mean, if I forgot to simplify, I would just do it when I was doing the limit, right? So what do I have here, right? So this x canceled away, but I have this, right, this factor here. So I end up with, right, plugging in 0 for x. I have 0 in my numerator over 2 times, who cares, except it's not 0, right? So you put 0 in here, negative 2, right, times 4, which is 0, which is finite. And then over here, right, canceling out the x over 2, I just have whoops, I forgot an x here, didn't I? So 2x, x minus 2 to the first, because I canceled out this x minus 2. Now I'm going to plug in, oh wait, can I cancel something out here, right? I have 2 x's there, but that's going to cancel with this one here. So I have x on top of 2 times x minus 2. Now plug in your 0, and again you get 0, which is finite. So both limits were finite, therefore, as we saw before, this singular point is regular. Let's do the same thing for my next singular point. So remember, don't forget to change, right? And now what happens when I evaluate these limits, right? This does cancel out. I have an x minus 2 to the first, which cancels out with that. But when I plug in 2 now, I do get a 0, right? So I get an undefined. I get a 3 over 0. But talk to me about, don't just say undefined, right? Here, because we're talking about a limit. So this is really 3 on top of, right? On top of, you put 2 into here and you get 2 times 0, which is 0. But really think about this graphically. Doesn't this mean, right, the factor didn't cancel out with something in the numerator? So graphically, what appears here? A vertical asymptote, which means you have a shooting off to positive or negative infinity, right? So not a finite limit. And again, I don't really care what happens over here, although I think you can see that the same thing would but again, I don't care what happens here, because once I got a not finite limit, I know this must be an irregular point. Okay, so the limit work verifies what kind of like that shortcut does, but please feel free to use the shortcut. So this equation is kind of famous. It is Bernoulli worked with it, and then Bessel. Bessel made it more famous. He did a lot. This equation has a lot to do with complex numbers, and then some also physics stuff, but I kind of forgot what the physics stuff was. But you can look it up if you want. But look at, I wanted to try to get this, I tried to embed this, but it just failed. I couldn't get it to work so that it would be animated. But look how cool this is, right? Look at that. Isn't that awesome? I think that's so cool. Anywho. Ah, sorry. Wrong PowerPoint. Nah. Sorry, kids. Why can't I make this go away now all of a sudden? There we go. Okay, so this one should not be very difficult, right? You're dividing through, right, to get it into. So hopefully you can see that your only singular point is at 0. And all that means all other points are ordinary. And I can look at now, if I just kind of skip my limit work, right? You're looking for the factor x minus 0 to the n in y prime. I have nothing to simplify, right? So already this is, right, this is bad news for me, right? Because what is n in your denominator here in front of y prime? n equals 2. So 0 is an irregular singular point. That's all there is to that. Here's another famous equation. This guy's picture is freaking hilarious. This guy's name is Legendre, not Lagrange, Legendre. And he's also a French guy. And if you go to his Wikipedia page, the sketch that they have on him is even more frightening than this, right? I was I cracked up so hard. I just could not believe what they had on the Wikipedia page. So he reminds me a little bit of Snape, doesn't he? Anywho, Legendre's equation. Oh, I looked up what this was for. Now I forget. Sorry. Short-term memory. So anyway, how about this one? You're going to divide through by 1 minus x squared. Right? So that's your coefficient of 1. So x is equal to plus and minus 1 are your points of singularity. I guess I should write this out as x equals negative 1 and x equals 1. So you are looking for your powers. In your denominators. And of course I would factor this. So this would be 1 minus x and 1 plus x. So I see x plus 1 to the first power in front of y prime. And I see x minus 1, not at all, or just the negative of it, but still only to the first power. So both of these are regular, yes? And all others are ordinary. I'm so confused as to why they don't have enough. Why of all, everybody else looks dour, but they at least look, I don't know what I think about this. All right, check out this. This one doesn't have a name, so there's no, nothing with it. No picture with it. But here you are dividing everybody by x squared minus 9, right? So in this case, my singular points, right? I have issues at negative 3 and 3. Now what kinds of issues are there? So this time I need to be a little careful. And actually kind of write these out, right? So underneath here is x plus 3, but so is x minus 3. Ooh, I knew there's something weird about this. Did I mess up that other one too? This is squared, and I forgot to put that up there. Sorry. So I am multiplying, I am dividing through, I'm sorry, by x squared minus 9 squared, but that of course is x plus 3 times x minus 3 times x plus 3 minus times x minus 3, which means that I have x plus 3 and x minus 3 twice. Right? So what does that end up looking like when I simplify? Well, here, the x plus 3 factor cancels out here and leaves a coefficient, I'm sorry, a power of 1. Here, nothing cancels out. So what does that mean for my decisions? X minus 3, when I look at the power x minus the singularity, how many times does x plus 3 show up in the denominator of my y prime? What is n? N is equal to 1, right, for x plus 3? And how about x plus 3? What is n in the denominator of the y coefficient? X plus 3, n is equal to 2. So don't I meet the conditions? Right? Since I meet the conditions, x minus 3 is a singular point, but it is a regular singular point, right? How about 3? Look at the factor x minus my point of singularity. How many times does it show up in the denominator of y prime? So who cares? Right? This breaks the rules. So x equals 3 is a point of singularity, but it is irregular. So, what do I do for... Are those your new ones?
I'm playing around too much. I guess, yeah.
Oh, boo.
No. Yes.
Let's try another one. Another problem. I'm doing a video. Say hello, Mr. Getz.
Hi, how are you?
He didn't realize I was videoing. Okay, so try this one. This one again, not too bad, hopefully, right? With the algebra, you see that I'm just dividing by x cubed. So my only point of singularity is 0. So you're going to look at when does the factor x minus your point of singularity n appear in the y prime, in the denominator of y prime. Well, don't forget to cancel, right? Don't forget to simplify. So this is just x to the first. So everything's okay. But what about here? Right? How many times does x minus 0, what is my n in the denominator in front of y? There was nothing to cancel this time. So breaks the rules. So x equals 0 is irregular, an irregular point of singularity. One more. How about this one? Notice I don't have any y prime. So, but how many points of singularity do I have? Two, right? So 2 points of singularity. So now I need to, right, this, remember I did this already, so that goes to 1. So how many times does, I don't have a y prime, so remember what my restrictions are. How many times does the factor x minus the point of singularity of n appear in the denominator? I don't have a y prime, so just denominator of y. right? N just equals 1. Good to go. X equals 0 is a regular point of singularity. How about x minus negative 3 to the n, which is really x plus 3. Now remember, you're looking at the denominator of y, so when you see there's no canceling to be done, so when you see this is n equals 2, you might be tempted to say this is a bad news. But remember, since it's in the denominator of y, we didn't have any y prime to consider. You're allowed to have n equals 2 or less in the denominator of y. So n equals negative 3 is also regular. Okay? All right, so that's it for this, for regular and irregular singularity points. So your homework shouldn't be that taxing at all. Again, if you want to go ahead and practice the limit work, the key online does the limit work with all of them. But know that when you are assessed, which you won't be anyway this year, but had you been assessed, we wouldn't ask you to do the limit work for every single problem. Okay? All right. Have a great day and talk to you soon.